have two formula on Laplace transform. The Laplace transform of delta function of t minus t0 is going to be e to the negative t0 times s. For t equal to 0, you have Laplace transform of delta of t is going to be equal to 1. Okay. Now let's go back to Laplace transform table. So you have number 14 here. So that's the one that you're looking for in terms of direct delta functions when you find Laplace transform. Okay. So when you find Laplace transform of delta of t minus a for a is greater than or equal to 0, so it's covered the two formula that I just wrote down. In the case of a equal to 0, you have Laplace transform of delta of t is going to be equal to 1. When a is greater than 0, then Laplace transform of delta of t minus a is equal to e to the negative as. Okay, so let's do some example on this. So you want to find the solution of the initial value problem. The setup is that you have y double prime plus 6y prime plus 5y equal to 3 times delta t. The initial condition is that y of 0 equal to 1 and y prime of 0 is equal to 0. So when y of 0 equal to 1, you can think of that as the locations. Initially, you add the location, let's say, 1 unit from the origins. And y prime of 0 equal to 0, you can think of that as the velocity, the initial velocity is equal to 0. That means you have a ball, you drop the ball, equal to 0. Okay, so to find the solution of this initial value problem or with this differential equation, you take Laplace transform on both sides of the equations. So the good thing about Laplace transform, now you can clearly see that you cannot use the undetermined coefficients. You cannot use variations parameters. The only case that can handle this type of forcing term is the Laplace transform. Okay, so take Laplace transform on both sides of the equations. Equal to Laplace transform of 3 times delta t. So you apply the properties of Laplace transform. Again, Laplace transform is a linear operator. So Laplace transform of the sum is the sum of Laplace transforms. So you have Laplace transform of y double prime plus 6 times Laplace transform of y prime plus 5 times Laplace transform of y. Also on the right hand side, you can move 3 out of the Laplace transform operations. You have 3 times Laplace transform of delta t. So Laplace transform of delta t is equal to 1, as you can see in the formula right here. So the right hand side is just going to be equal to 3. Then you'll apply Laplace transform for derivatives. So Laplace transform of second derivative is s squared times capital Y of s. So that is Laplace transform of little y. Minus s times y of 0 minus y prime of 0 plus 6 times Laplace transform of the first derivative, which is s times capital Y of s minus y of 0 plus 5 times capital Y of s equal to 3, which is the right hand side. So remember, y of 0 is equal to 1 and y prime of 0 is equal to 0. So this is equal to 0. This is y of 0 equal to 1, y of 0 equal to 1. So you substitute those informations into the equations. You get s squared times capital Y of s minus s plus 6 times s times capital Y of s minus 1 plus 5 times capital Y of s equal to 3. Okay. Now you distribute the 6 and then combine like terms. So s squared times capital Y of s minus s plus 6s times capital Y of s minus 6 plus 5 times capital Y of s equal to 3. Right. So capital Y of s is a common factor. You left with s squared plus 6s plus 5. And then you move negative s and negative 6 to the right hand side. You get, this is positive s plus 9. Now, to solve for capital Y of s, you divide both sides for s squared plus 6s plus 5. So capital Y of s is equal to s plus 9 divided by s squared plus 6s plus 5. So you move from the time domain, or you transform the information from the time domain to the frequency domain, and the solution in the frequency domain is here. Right? You have these fractions, and of course, eventually you want to turn this information back into the time domain to get the solutions little y of t. And to do that, you need to take inverse Laplace transform. Okay, an inverse Laplace transform of this type of fractions. Then you want to think about partial fraction decompositions, given that the denominator can be a factor of a linear factors or of the quadratic factor. Okay, so I'm going to factor this s squared plus 6s plus 5, and this is going to be s plus 9 over s plus 5 times s plus 1. Okay, you cannot do quadratic factor in the denominator for this case because the discriminant, the delta of this quadratic term is not less than 0. Right? This is still factorable. Okay. So to find little y of t, we apply the inverse Laplace transform on capital Y of s. That is, you get little y of t equal to inverse Laplace transform of s plus 9 over s plus 5 times s plus 1. Alright, so think about partial fraction decompositions. Consider the partial fraction decompositions. As follows. So you take this function and you separate this into two different fractions. So you have s plus 9 over s plus 5 times s plus 1 equal to capital A over s plus 5 plus capital B over s plus 1. Right? Because the factors in the denominators are linear factors, that is why you separate this in this form. Okay. Now, on the right-hand side, when you combine two fractions together, you find the common denominator. You have s plus 9 over s plus 5 times s plus 1 equal to a times s plus 1 plus b times s plus 5 all together divided by s plus 5 times s plus 1. So the denominators are the same now, you just match the numerator together. Okay, so move to another page. So you just match the numerators together. So you have s plus 9 equal to a times s plus 1 plus b times s plus 5. When s is equal to negative 1, what's going to happen? You have negative 1 plus 9 equal to a times negative 1 plus 1 plus b times negative 1 plus 5. Doing this allowed one of the constant or one of the parameters to disappear. So this capital A disappears and you can calculate the value of B. So here you have positive 8 on the left. This is 0. And you get for B, therefore B is equal to positive 2. Okay. Now when S is equal to negative 5, you get negative 5 plus 9 equal to A times negative 5 plus 1. Plus b times negative 5 plus 5. So the left hand side you get positive 4 equal to negative 4a. This term is equal to 0, and therefore you can solve for a, and a is equal to negative 1. Right. And from here, so let me quickly recap what we just did. Right? So we're trying to find the inverse Laplace transform of these functions. We recognize that you can separate these fractions to two different fractions using the partial fraction decompositions. And we found the value of capital A and capital B. Now you put it back to find the value of y of t. Then the inverse Laplace transform is so you get a little y of t equal to the inverse Laplace transform of a over s plus 5 plus b over s plus 1, given that a is equal to negative 1 and b is equal to positive 2. So negative 1 over s plus 5 plus 2 over s plus 1. So inverse Laplace transform of the sum is the sum of inverse Laplace transforms. You get negative inverse Laplace transform of 1 over s plus 5 plus 2 times the inverse Laplace transform of 2 over s plus 1. Alright, so at this point you need to go to the Laplace transform table and look at this formula right here, number 15. So you have the inverse Laplace transform of 1 over s minus a, or in this particular case, you have inverse Laplace transform of 1 over s plus 5. So 1 over s plus 5. And again, you want to mimic the formula. That is, you want to have the subtractions in the denominator. So this can be written as 1 over s minus negative 5. Right? So a is equal to negative 5. Therefore, the inverse Laplace transform of this function is e to the negative 5t. Let me go back to the formula here. You have negative of e to the negative 5t plus 2 times inverse Laplace transform of, so I forgot about this, so this one is 2. You need to cancel out, it's just 1. So that one is 1. Alright, so inverse Laplace transform of 1 over s plus 1. And use the same formula, you got 2 times e to the negative t. So that is the solutions of the initial value problem given the differential equations of the form, of this form, and 2 initial conditions, y of 0 equal to 1 and y prime of 0 is equal to 0. Okay, so this is the functions that you see. That is the solutions that we just got, right? So what's going on with this curve? So forget about the curve, the left part of the curve. Let's just look at the curve going from 0 to, let's say, positive infinity, whatnot. So what's going on here? So initially, the position is y of 0 is, the initial velocity is y of 0 equal to, y prime of 0 is equal to 0. It gets shot up very quickly, and everything is going to go down eventually. Do you see that idea?
Yes.
Alright, so what's going to happen? What is the scenario here? I don't know if you have this one, but bear with me here. Have you ever seen a type of door when you kind of like shut it very quickly and then just leave the room, but it's not fully closed with the moment that you go out of the room? It just slowly, at first it just shut it very quickly and then slowly close it. Do you have something like that? So you or you have seen a door like that before?
Yeah, it's got a dampened spring, so now when you close it,
Exactly.
it closes to a point, and then it slowly decays closed.
There you go, there you go. There. So this is the type of system that you're going to see for the type of door that the damping, that's some damping in there, right? So it's very quickly close it, like that's why the velocity shot up to this peak a little bit, but eventually it slow down and go to 0. You okay with that? Alright, so that's just the one scenario that you're going to see. Now let me move on to another example. So let me move on to this example. You have the initial value problem of y double prime plus 9y equal to 3 times delta t minus pi. Same initial conditions. Okay, let's see what happened in this scenario. Right, so similar to the last example, what you do is you do apply Laplace transform on both sides of the equations, of the differential equations. So you have Laplace transform of y double prime plus 9y equal to 3 times Laplace transform of delta t minus pi. So Laplace transform of the sum is the sum of Laplace transform. So Laplace transform of y double prime plus 9 times Laplace transform of y. On the right-hand side, you have Laplace transform of delta of t minus pi. So you go to Laplace transform table. You go to this formula right here. So Laplace transform of delta, you have e to the negative t0 times s. For t0 in this case is equal to pi. So go back here, you have e to the negative pi s. On the left-hand side, you still need to take care of Laplace transform of the derivative. So that is s squared times capital Y of s minus s times y of 0 minus y prime of 0 plus 9 times capital Y of s equal to 3 times e to the pi s. Okay. So y of 0 is equal to 1 and y prime of 0 is equal to 0. So y of 0 is equal to 1. Y prime of 0 is equal to 0. So you have s squared times capital Y of s minus s minus plus 9 times capital Y of S equal to 3 times e to the negative pi s. So on the left hand side, capital YS is the common factor. You're left with S squared plus 9. And negative s, you move to the right hand side, you get s plus 3 times e to the negative pi s. Now to find capital Y of s, you divide both sides for s squared plus 9, or s over s squared plus 9 plus 3 times e to the negative pi s divided by s squared plus 9. Now you're going to take the, so this is the solutions in the frequency domain. And to turn this into the time domain, you need to find the inverse Laplace transform. So to find y of t, we take the inverse Laplace transform of capital Y of s, that is, you have little y of t equal to inverse Laplace transform of s over s squared plus 9 plus 3 times e to the negative pi s over s squared plus 9. So inverse Laplace transform of the sum is the sum of inverse Laplace transforms. You have inverse Laplace transform of s over s squared plus 9 plus 3 times inverse Laplace transform. Actually, let me leave the 3 in there. So inverse Laplace transform of, let me do this, e to the negative pi s times 3 over s squared plus 9. Okay. So the first inverse Laplace transform is straightforward. You go to the Laplace transform table here. You go to this equation, or this formula. You have s over s squared plus b squared, for b is equal to 3 in this case because you have the formula of, or you have the function of s over s squared plus 9. So b is equal to 3 in this case. So the inverse Laplace transform of s over s squared plus 9 give you cosine of 3t. Let me go back to the note. So the inverse Laplace transform of this function is cosine of 3t. Now, for the second inverse Laplace transform, you go back to the last lecture when we talked about the Laplace transform in inverse Laplace transform of step functions and unit step functions, or shifted unit step functions. And you can rewrite this particular function as follows. So the inverse Laplace transform of e to the negative pi s times Laplace transform of sine of 3t. Okay, so let me go back to the last lecture. So lecture 16, where you take, when you work on something like this, right? So this is very similar to what we're working with, okay? Except you have a different Laplace transform here. So you, here in this example, you have s over s squared plus 9, but the problem we have right now is the functions of 3 over s squared plus 9. Okay, let's go back to here. So therefore, this is sine of 3t. And when you apply the inverse Laplace transform, you're going to have u of t minus pi. So the shift now, or the value of c, is equal to pi. Therefore, you have u of t minus pi times sine of 3 times t minus pi. So that's the solutions that you're going to get. Okay, 2 plots. So the first one is the solutions y of t. You think about the precision functions. And on the right hand side, you have the velocity functions, so y prime of t, right, when you take the derivative of the function. So in this functions, you can see that there's 2 parts to this. One part is the cosine function, which is for the case of actually the combination of cosine function and sine functions when t is less than pi, and purely for the sine functions when you have when t is greater than pi. So there is the impulse happening in the middle here in the case of t equal to pi. Okay, you can think of this scenario in the case of a speed bump, right? As you move along here, you drive the cars, given that you ignore all the factor and you have a very smooth drive. but momentarily at the moment of t equal to pi, you have a speed bump, and therefore there's a kind of like a hint here that occur at t equal to pi. And to get over that speed bump, what you do is that you cannot drive the normal velocity, normal speed anymore. What you do is you have to quickly accelerate to get over that speed bump. So that's there a shot at the velocity, shot up at the velocity. And that is kind of the explanation for this type of solutions that we got.